In this video lesson, we're going to continue on from valence bond theory, so hopefully you've already watched that video. In this video lesson, we're going to be talking about hybridization. Hybridization is a really easy concept, but what this video is going to do is it's going to show you the idea behind it so you understand the concept. Okay, so let's take a look at a following molecule, BeCl2. Now, according to valence bond theory, the central atom needs to have enough bonding sites in order to accommodate the terminal atoms that are trying to bond with it. In other words, you have BeCl2, so you have beryllium as the central atom, and you have two chlorines that are trying to bond to that beryllium. So according to valence bond theory, beryllium would need to have two bonding sites, one for each chlorine, in order to make this happen. In other words, it would need two orbitals, both of which have one electron, or half-filled. Now, if you take a look at the ground state configuration for beryllium, which is shown up here to the top right, you can see that beryllium actually has no space for chlorines to bond. You see the 2s is completely filled, and then the 2p are completely empty. So according to valence bond theory, there shouldn't be any bonding happening with beryllium. So how is it that two chlorine atoms can actually end up bonding to beryllium? The answer is hybridization. Hybridization is the mixing of atomic orbitals. If you think about the word hybrid, it's a mixing of two different types of things. So here's what actually ends up happening. There is a promotion of the electrons that are in the 2s orbital here, and one of those electrons moves here to the 2p, and that's shown in this process right here. That one electron moves into an empty p orbital. When that happens, the s as well as that one p orbital mix. And when they mix, they create a hybrid orbital that now, if you look, has that two bonding sites for the chlorine. One chlorine will bond to this orbital, and one chlorine will bond to this orbital. Since these orbitals were mixed using the s and one of the p orbitals, that is why it's called an sp hybridized orbital. To look at it from a color scheme perspective, you recall that the s orbitals were always yellow, and the p orbitals were always that bluish purple color. And so since hybridized orbitals are a mixture of s and p, you can see that the coloring would be green. So anytime you see green orbitals, whether it's in a textbook or on a worksheet, know that they're looking at hybridized orbitals. First example may have made little to no sense at all. Totally understandable. By the end of this video, hopefully you're going to understand because we would have seen so many examples. So let's look at another example. Let's look at the compound BF3. So the Lewis dot structure for BF3 looks something like this. I'm excluding the lone pairs on the fluorines to just show the general idea. Okay. So according to valence bond theory, in order for this molecule to actually happen, there needs to be three bonding sites on boron in order to accommodate the three fluorine atoms that are trying to bond to it. So if we draw the ground state configuration for the central atom boron, you can see that there's actually only one space or one bonding site for a fluorine, and it's right here. That's not enough. Boron needs three bonding sites in order for these three fluorines to bond. So what happens is there's this promotion, and remember the promotion is one of the electrons here in the 2s orbital gets promoted to the next empty orbital, which would be right here in the center. So what happens is that one electron moves right there, and as a result you end up getting this promotion. The asterisk next to the boron indicates that it is in some sort of promoted state. So now you have one electron in the 2s, and then you have one electron in each of the p orbitals here. So what happens is those orbitals mix, and as a result they create the hybridized orbitals that you see here that are now in green. Now, what did it take to make these hybrid orbitals? It took the s orbital as well as two of the p orbitals, which is why the hybrid orbital is now called sp2. As a result of the mixing of the orbitals, you now have 1, 2, 3 bonding sites for the three fluorines to come in and bond. And well, that makes about 5% sense, but I'm still not tracking. That's totally okay. Let's look at another example. Let's look at methane, CH4. CH4 has the Lewis dot diagram like this. It has carbon, bonding to 4 hydrogens. So according to valence bond theory, carbon needs to have 4 bonding sites in order to accommodate 4 hydrogens. When we draw the ground state configuration for carbon, which you see right here, notice it only has the 2 bonding sites. So as you may have guessed, there needs to be an electron promotion. One of the electrons here in the 2s is going to get promoted to the next empty orbital, which is going to be right here. As a result, this is the promoted state of the carbon electron configuration. When we mix those orbitals, we get our hybridized orbital that's over here. So the hybridized orbitals were made from a mixture of the 2s as well as the 3 individual p orbitals here. So, as a result, the name of the hybrid orbital would be sp3 because it was made from an s as well as 3 of the p orbitals. Alright, another example, PCl5. If I were to draw the Lewis dot structure for PCl5, it's going to look something like this. It's going to have an expanded octet, which it is allowed because phosphorus is in row 3 or higher. And so it's going to look something like this. So in order for this molecule to actually happen, phosphorus needs to have 5 bonding sites to accommodate all 5 chlorines. Alright, if we draw the if we draw the ground state configuration for phosphorus in the center, we're going to get something that looks like this. Alright, according to the ground state configuration, there are 3 bonding sites, okay, 1, 2, and 3, to accommodate 3 chlorines. But, as you can see, we need 5 bonding sites. So, as always, one of the electrons here is going to get promoted. But you can see that the next empty orbital actually is not in the p, because all p orbitals have at least 1 electron in them. So the next available open orbital then would be above that, which in terms of Aufbau's principle, or the energy level, would be the 3d, which are currently empty. There's no electrons there. So the electron actually goes completely past the p orbitals and goes all the way here to the empty d orbital, which would be next. So after the promotion here, you would see that this is where the electrons are actually being at. So mixing the orbitals that are needed, we mix the s, the 3p orbitals, and then that 1d orbital. So when you mix all of those, you get your 5 identical hybrid orbitals, now that all have enough electrons in the proper spots to have the bonding sites for 5 chlorines. 1, 2, 3, 4, and 5. When we ask ourselves what orbitals were needed to make such a hybrid orbital, it took an s, it took 3p, and it took 1d. So the name of it would be sp3d. I forgot to mention this, but hopefully you've seen it from the examples, that notice when we write the number 3, or any number for that matter, it's always a superscript. It's not a subscript. Okay, so hopefully you're starting to kind of catch on a little bit more. Let's look at the molecule SF6. Sulfur is our central atom, and then you've got 6 fluorines. And by the way, it's really important to draw the Lewis diagram from scratch. I'm kind of drawing them for you to be quick about it, but you always have to make sure you draw it because you never know if there's a lone pair on the central, and that's going to be important. You'll see that when we do an example in a couple slides here. Okay, so this is the Lewis dot structure for sulfur hexafluoride, or SF6, and notice the way it's drawn, there needs to be 6 bonding sites to accommodate the 6 fluorines that want to bond. Drawing the electron ground state configuration for sulfur, how many bonding sites are available right now? There's only 2, here and here. So what's going to happen is there's going to be a promotion. This electron right here is going to first get promoted to an empty d orbital, but if we only do that, there's only going to be 4 bonding sites. This one would have 1, 2, 3, and then 4. So we're going to have to do another promotion of this electron to the next empty orbital. So after we promote both of these electrons to the empty orbitals in the d, you end up getting this configuration over here after the electron promotion. Now we have 1, 2, 3, 4, 5, 6 spaces available for bonding. Hybridizing all of those and mixing them together gives us the hybrid orbital that now has the 6 identical hybrid orbitals that now have enough spaces for the fluorines to bond. It took the s, the 3p, and then 2 of the d's in order to make it, resulting in an sp3d2 hybrid orbital. Alright, now that was the concept of hybridization. Hybridization is actually very simple because if you think about it, all the hybridized orbitals are going to be based off of the electron domain geometry. So I'm actually going to do this off to the side here for a second. If you recall from our molecular geometry lecture, we talked about how you can have electron geometry of 2, 3, 4, 5, and 6. 2 was going to be your linear, 3 was your trigonal planar, 4 was tetrahedral, 5 was trigonal bipyramidal, and then 6 was octahedral. The hybridization is going to come directly from your electron domain geometry, or in other words, how many electron domains you have. So, remember, from all of our examples, what was the maximum amount of S's that you could have? It was 1, right? What was the maximum amount of P's you could have? It would be 3. Whether you used them all or not, there were 3 available. And then if you needed to use the D's, there were a maximum number of 2. So you're always going to have the general form of S, Px, depending on how many you need, and then dy, depending on how many you need. So you're always going to just count up how many electron domains, and that's going to be the number of S, P's, and D's that you would have. So that may make no sense right now, but let's look at an example. Let's suppose you figure out that a certain molecule has 2 electron domains, so it's linear. Okay, well, you're going to start with S, and there's only one option for S. You can only have 1. Okay, we need to have a total of 2, so the next letter would be P. And since that is 2 right there, it's S and P, that would be your hybridized orbital, SP, because there's two that are already being used. Okay, let's look at 3. This may make no sense, and I'm hoping it will in just a moment. Let's look at if you determine that a molecule has 3 electron domains. So that'd be trigonal planar. Okay, so you start out with S, okay, but that only takes care of one of the 3. Your next letter is P, and then how many would you need? SP is only 2, so we would need an SP2 in order to get your 3 total that's needed. Okay, let's look at tetrahedral. Okay, tetrahedral is 4 electron domains, so you're going to have to start off with an S, that's one of the 4. The next is P. Are you going to need all 3 P's? Yes, because total between an S and then the 3 P's, that's where you get your 4 electron domains. So a tetrahedral molecule would have sp3 hybridized orbitals. Okay, let's suppose you have 5 electron domains. Starting off with the S, there's one of the 5. P, but remember, there's only a maximum of 3. So right now with sp3, you've only taken care of 4 out of the 5 electron domains. So where's the 5th one going to come in? That's where you have the D. Oops. There we go. So you would have sp3d hybrid orbitals. Finally, if you have determine that a molecule has 6 electron domains, that's going to be S, which takes care of one of the 6. You're going to have P3, so now there's 4. D, but then you need 2 of them in order to get the 6. The hybridization or the hybrid orbital needed will always relate to the electron domains. So as soon as you figure out how many electron domains a molecule has, then you know what the hybrid orbital is needed. So that goes along with the steps that we see here to the right. If you ever are trying to show the steps for hybridization, the first thing you're going to do is you're going to draw the Lewis structure. You're going to count the number of electron domains, just like we would have when we were trying to figure out geometry. Once you do this step, this is going to tell you the hybrid orbitals needed. Then you'll be able to determine, you're going to be able to determine the hybrid orbital needed based on the number of electron domains. And then you'll actually be able to draw the ground state configuration and place the electrons in hybrid orbitals one at a time as needed. All right, this may be clear as mud right now, but let's do an example. Okay, use hybrid orbital theory to explain the bonding in BRF5. Based on the previous slide, the first thing we need to do is we have to draw the Lewis dot structure. Okay, so I already know that bromine's going to be in the middle, and we're going to have 5 fluorines around it. 3, 4, and 5. Okay, let's figure out how many valence electrons total that I have. Bromine has 7. Fluorine has 7, but there's 5 of them, so that's going to be 35. And so if I add those together, that's going to give me 42 valence electrons. If I do a single bond between all of the fluorines, that takes care of 10 of my 42, so I'm left with 32 valence electrons. I'm going to start placing these on the terminal atoms for fluorine. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So I just use 30 of the 32. So I have 2 electrons left over. Based on my rules for Lewis dots, I need to place them on the central. This is why it's so important to draw the Lewis dot structure first before you try to do any sort of hybridization, because you don't know if there's a lone pair on the central, which in this case there is. Okay, so now that we have the Lewis dot structure drawn, what is the number of electron domains that are around the central? The answer is there's 6. 5 of them happen to be bonded, but then the 6th one is the lone pair. So there are 6 electron domains. Write it out here. There are 6. Sorry about that. 6 electron domains. So when you have 6 electron domains, which is an octahedral shape, by the way, for your electron domain geometry, you say, okay, what hybrid orbital corresponds to 6 electron domains? You can remember it, or you can just count them out. There's 1, P3 makes it 4, D makes it 5, and then D2 makes it 6. So there would be an sp3d2 hybrid orbital that's needed. Okay, now, if I just asked you what hybrid orbital is needed, this problem would be done. But I'm asking you to use hybrid orbital theory to explain the bonding. In other words, I'm asking you to show it. Okay, so let's go ahead and do that. So just like we did before, I'm going to draw the ground state configuration for bromine. Okay, so here is the ground state configuration for bromine. Just real quickly, you'll notice I don't write, so it goes 4s2, 4p5. You'll notice I leave out the 3d because the 3d is in a lower energy level, so it's not going to be something that's going to be dealt with in the hybridization process. So we have 4s2, 4p5, and then 4d is empty here, but that's kind of a hint. We're going to need it. Because if you look at the ground state configuration as it is, we only have one spot available for bonding. And we know, we already know that we need an sp3d2 hybridized orbital. We're basically proving it, okay? Because we already know that because if it has 6 electron domains, it's going to need this hybrid orbital. We're just going to prove it right now. Okay, so what I'm going to do is I'm now going to do my electron promotion. Okay, so I'm going to start here. I'm going to take this electron, and I'm going to promote it here. And then I'm going to take this electron, and I'm going to promote it here. So let's go ahead and take a look at what that's going to look like after the promotion. Okay, so notice after the promotion, which is written down here, the promoted state of bromine ends up having a single electron in all 3 of the p orbitals, as well as now in the 2. So what's going to happen is that s, all those p, and the 2d orbitals are all going to mix, and they're going to create hybridized orbitals. So now, if you notice, because of that electron promotion, you now have 1, 2, 3, 4, 5 spots available for bonding for the fluorines, and that's exactly what we need. We need 5 spots in order for those 5 fluorines to bond. Now you may be wondering, well wait, what about these 2 electrons? Why didn't that electron get promoted? Well, first of all, we don't need it to promote because we already have the 5 spots available for bonding, which is right here. But also notice that those 2 electrons right there, that's the lone pair. So the lone pairs are actually sitting right where they need to be, but they're all in a hybridized orbital. So the key thing to notice is that after the hybridization takes place, there are 6 hybridized orbitals total. But 5 of the 6 are available for bonding to another atom, and then the 6th one is housing the lone pair that we see right there. Let's do one more example together. All right. Check for understanding. Show the hybridization of the following molecule. Be sure to include what type of hybrid orbital is needed and the orbital diagram for the hybrid orbital. So first, let's start off with the Lewis dot diagram for XeF4. Okay, the first thing I have to do is the Lewis dot diagram, which I have here. I went ahead and drew it already for us because we've already seen this in class. But the important thing to note is that, look, there are 2 lone pairs. That's why you have to draw the Lewis diagram. So after drawing the Lewis diagram, how many electron domains does this molecule have? And the answer is 6. Remember, as soon as you know how many electron domains, immediately you know what kind of hybrid orbital is needed. And that would be sp3d2. Notice how that all adds up. Okay, 1s, 3 p's, and 2 d's all add up to give us 6. Now, I have to prove that it's sp3d2. So just like before, I'm going to draw the ground state configuration for the central atom, which is xenon. Alright, so here's the ground state configuration for xenon. As you might expect, being a noble gas, it doesn't have any bonding sites as it is written. So we're definitely going to have to do some promotion. We're going to have to do some promotion in such a way where we can make 4 fluorines bond to it. Alright, so I already know it's going to be sp3d2. So my guess is I'm going to have to take 2 electrons, this one as well as this one, and promote them. Alright, as a result of promoting those 2 electrons up here, we end up getting the 4 bonding sites that we need for the fluorines. And notice the 2 additional hybrid orbitals are going to house the lone pairs, which we see right there. So as a result of mixing, those 6 orbitals that we saw here, this is where we end up getting our sp3d2 hybrid orbitals that are needed for this particular molecule.